Welcome back. We finished the last lecture with the following integral, phi plus, which was the integral from 0 to 1 over r naught. Here we have 1 minus 2m over r naught, 1 over r naught squared, minus u squared. Remember, u was the variable 1 over r. We started originally with the r variable. U to the 3 du. And recall what we are trying to do. We are trying to find phi plus, because phi plus then controls the deflection angle of a ray of light that passes near the surface of the sun. And what we are trying to do today, we are trying to estimate this integral. In particular, we are interested in this integral assuming that m is small. This will make the integration much easier. So step 1, we will simply set m to be 0. Then this integral becomes quite simple. We integrate from 0 to 1 over r plus. This here is 0 to m over r if we set m to 0, which means we are left with 1 over r squared. By the way, there is a minus 1/2 missing up here, which might also be missing on the last line of the previous lecture notes, but we definitely carried this throughout most of the calculations. So there's the square root there. Minus u squared. We want to integrate over u. Minus 1/2. And I'll just write out the square root now explicitly. By doing so, it simply looks more familiar, and you can immediately see what this integrates to. 1 minus r squared minus u squared, which is a standard integral that you recognize. You have the square root of 1 minus u squared. You use a standard trigonometric substitution, and you find that this integral is arcsine r0 u evaluated between 0 and 1 over r naught. You know that the arcsine function is 0 at 0, and if we then evaluate this integral at 1 over r naught, what we get is simply the arcsine of 1, which is pi over 2, because sine of pi over 2 is 1. This means, hence, in the absence of any masses, we find the object we want to compute is delta phi. You need to just go back to the figure to reconvince yourself what this was. This was 2 phi 0, 2 times either phi 0 or phi plus at the same angle up to a sine, minus pi. You might be wondering, why did I subtract pi? The answer is the result when m is 0. We now get 2 times pi over 2 minus pi, which gives exactly 0. If I provide you with a very quick sketch of the figure that we had, the figure we had is we had here our light ray passing by the sun, and here we had our asymptotes that these lines approach to. And this angle here was precisely delta phi. If you now think about this, if the light does not get deflected by the sun, then it simply travels on this trajectory. which means the second asymptote overlaps with the first asymptote, and this angle delta phi approaches zero. Exactly consistent with our result. We are now interested in the leading order contribution that m makes to this integral. There are different ways how to do this. Step 2. So there are different ways how to evaluate an integral like this when m is small. The easiest way is to think about a Taylor series type expansion. Step 2 is consider phi plus is obviously a number because it is a definite integral. So this is some kind of number, and this number will depend on m. What we do is we consider or we view phi plus as a function of m. And now assume m to be small. What I'm really trying to say here, recall that 2m over r naught here is usually our physical mass that appears in the Schwarzschild solution. This guy has units of length. And again, we are assuming that this is much smaller than any radius we are working with. I said this when we looked at this integral. Recall that we are integrating between 0 and 1 over r, but r0 itself is already very large. So therefore 1 over r0 is very small. So we are only integrating over small values of u. So this is much, much smaller than 1 over r, than r naught, or we can also say that this is much less than 1. And we estimated this for the mass of the Sun, this was around 10 to the minus 5. If we view phi as a function of m, we can now write down a series expansion. This means we are saying that phi plus of m is phi plus when m is 0 plus d phi plus dm. Now we are setting m to 0 multiplied by m plus terms which are quadratic in m. This is really the first term in your Taylor series expansion around the origin. You write f of 0 plus f prime of 0 times x and so on, where the mass now takes the role of m. This is quite efficient. We can simply hope that this integrand here, when we apply differentiation with respect to m, becomes simpler. So let's try this. We have f plus of m was this integral from 0 to 1 over r naught. If we look at what we actually have here with m, we have 1 over the square root of this function here. So du square root. It starts with this constant factor here minus the u squared term. I just start writing this out. 1 minus 2m over r naught dot 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 dot, and the last term here is it minus or plus 2m. This means we need to differentiate this function. Let us do this. D over dm of one minus m over r naught, 1 over r naught squared minus u squared plus 2m u to the 3 to the minus 1/2. And recall, we need the derivative, and then we want to evaluate this when m is 0. Just check that we've written the right thing down. That looks good. Clearly, when we differentiate this object here with respect to m, we don't get anything because it's not a function of m. Let's start with a new page. First, we need the chain rule, minus 1/2, 1 minus 2m over r naught, 1 over r naught squared minus u squared plus 2m minus 3 over 2, because you reduce the exponent by 1, times the inner function with respect to m. That's the important bit. M here is our independent variable in this approach. Which means this factor here, 1 times 1 over r squared, differentiates to 0, which means from this first term here we get minus 2m over r linear function, and m differentiates, gives 2 over r naught times 1 over r naught squared. This object here differentiated with respect to m gives 0, and here we then get 2u to the 3. And as in the line above, all this is still evaluated when m is 0. This factor here doesn't depend on m anymore, but there are m's left in here, which means we can now simplify this. Minus 1/2. If m is 0 in this term, we are left with 1 over r0 squared minus u squared plus 0 minus 3 over 2. And here we have minus 2, 1 over r0 to the 3 plus 2u to the 3. We now have all the terms that we need. You see here that the 1/2 cancels those 2's, and there is a minus sign here. One over r0 squared minus u squared minus 3 over 2. And here we then get this minus times this minus becomes a plus. 1 over r0 to the 3, and this plus becomes a minus because of this minus. And therefore, this first term here in our Taylor series expansion gives d over dm of phi plus evaluated when m is 0 is now given by the integral between 0 and 1 over r of this function here that we've just written down. One over r0 to the 3 minus u squared over the square root of 1 minus r0 squared minus u squared du, because this is the variable over which we integrate. Some of you might think, hang on a minute, this integral here is not much better than that integral. However, if you look at the integral that we found when m was 0, we could use a standard trigonometric substitution to evaluate this exactly, because we are still left with exactly the same term here in the next to leading order bit, so the bit that comes with an m. By the way, this is not a square root. This is, well, it is a square root as well. But I have to be careful. Better write this like this. So there's -3/2 here. Apologies for that. So to get rid of the square root factor that appears here because of the 1/2, it makes sense to again use the same trigonometric substitution that we've used before. So let me show you how you would start attacking this integral. And to solve this, let us set u equals 1/r0 sine of alpha. This gives us that du is 1/r0 cos alpha d alpha. Now we have that u equals to 0 will correspond to alpha equals 0. We have a definite integral, so we need to be careful with our limits. And u equals 1/r0 corresponds to sine of alpha being 1, which means alpha has to be pi/2, which is, it's not really a coincidence that this is the same that we find here. Which means our integral, let me just call this I. Our integral now becomes the integral from 0 to pi/2. Let's make the substitution. 1/r0 squared, no, to the power 3, minus 1/r0 to the 3 sine to the 3 alpha. Here we have 1/r0 squared minus 1/r0 squared sine squared alpha to the power, of course it's down there, it's a plus, to the power 3/2. And our du, which is back here, was 1/r0 cosine alpha d alpha. Zero to pi/2. We now can pull out a factor of 1/r0 squared, which we take the square root of, giving us effectively a factor of 1/r0, which then gets raised to the power 3. So it is 1/r3, r03, which is exactly the same as these prefactors here, which means these terms all cancel. However, this one remains. We have hence a 1/r0 term here. On the top here we have 1 minus sine to the power 3 alpha. And down here we have 1 minus sine squared, which we can immediately write as cos squared. Then we take the square root. Let's do this slowly. Cos squared alpha to the power 3/2 cos alpha d alpha. The 1/r is the one which is there. We can now take the square root raised to the 3rd power and then divide by one of those powers. Our integral now is 1/sine to the 3 alpha divided by cos squared alpha d alpha. So you see we are making our way slowly and slowly towards solving this integral. At this point you have again a few different choices. You could, for instance, split this up into 1 over cos squared plus minus sine to the 3 over cos squared, and then integrate 1 over cos squared to give you tangent alpha, and then deal with this one separately. The most efficient way when you see an integral of this type is next to use the tangent half angle substitution, tan alpha over 2. This will rationalize the function, rationalize the integrand to get you a rational function. If you do this, you will arrive at the following integral, so please do check this. This will become the integral from 0 to 1 of 2 over 1 plus t squared here plus 4t over 1 plus t squared squared. And if you then integrate this, you eventually find that this whole integral is nothing but 2 over r0. So what you need to show is that this integral here is 2 if you work either with alpha, or that this one is 2 if you work over t. So if your integration isn't that solid and you haven't seen these substitutions done for a while, just work yourself through this. So this means that our phi plus of m, we now need to go back to all our results. So our idea was to write a series expansion. Phi plus when m is 0 was the first result here, which is pi over 2. And the second result is the one we've just computed here. So let's put this all together. We have phi plus of 0 plus d phi plus over dm evaluated at 0 times m plus higher order terms. We found that this first term here was pi over 2 plus 2 over r0 m. I strongly recommend that you go through this integral, especially if integration isn't your favorite part of the mathematical methods that you have learned, which implies that delta phi, which was 2 phi plus minus pi, essentially set up in such a way that this pi term disappears. We then get 2 pi over 2 plus 2 over r0m minus pi. Let me now write here approximately, because I don't want to write plus terms of order 2. We already know that 2 times pi over 2 minus pi gives us 0, which means we get 4m over r0. Or in physical units, I'm just saying with units, but what I mean by this, I'm writing it in such a way that all the units are the canonical units of the object. In which case we get 4g m over c squared r0. which is, if you look at this, very similar to the object that actually appears in the Schwarzschild solution. In the Schwarzschild solution in physical units, we get 2gm over c squared r0. To apply this to the sun, or to a light ray passing by near the sun, we will do the following. For light rays passing near the sun, we have m is obviously then the mass of the sun, and r0 can be approximated to be the radius of the sun. Some of you might think, well, isn't that a pretty strong approximation? And doesn't that mean that the particle has to be, or the light ray has to be very close to the surface of the sun? Well, in a sense, yes. But even if you are a few hundred kilometers away from the surface of the sun, it is still pretty close compared to the radius of the sun, which means the mistakes you make are again very small. And so this implies that our delta phi for the sun is 4g times the mass of the sun divided by speed of light squared times the radius of the sun. And if you pop this into a calculator, you will find 8.5 times 10 to the minus 6. Recall that this object here by construction is dimensionless. And astrophysicists like to count angles, not in these dimensionless units, but in arc minutes and arc seconds. So if we work this out, you get roughly 1.75 arc seconds. And this deflection angle was first observed by Eddington. So he led the solar eclipse expedition in 1919. You think about this, this is only 4 years after Einstein formulated his theory. So a lot of people were convinced that this would be a worthy expedition. And we should also say that from an historical point of view, so this was the first experimental observation of a prediction by general relativity. And this is why this is the one I always teach first, because it was the first direct observation. If you think about the perihelion precession of Mercury, I'll say a few words about this in another lecture. Then while the perihelion precession was known and the amount of precession that couldn't be understood from Newtonian physics was also well known, I think the skeptic towards general relativity would have simply said, well, it is just an accident that the number comes out right. It's nice, but an accident. However, for light deflection, there is a Newtonian prediction and a general relativistic prediction, and they differ. And so it is a direct evidence that you can't put this down to luck, really. This is a very good, a very strong evidence towards this. Let me make two more comments about this. So first of all, I've always talked about a light ray passing by near the sun. And I'm teaching it in this way because it was, again, the first way this was observed. From a modern point of view, you don't need light. You just look at electromagnetic radiation that comes in and passes by near the sun, and you can do this these days on a pretty much on a constant basis. So you don't have to wait for a solar eclipse anymore, because you only need a solar eclipse if you rely on the optical spectrum. If you are interested in electromagnetic radiation outside the spectrum, then of course you don't have to wait for an eclipse, because the electromagnetic radiation in many frequencies doesn't really mind the sun being there or not. So we can now observe this constantly and very precisely, and the evidence is overwhelmingly in favor of this angle predicted by general relativity and not the Newtonian angle. But here comes the interesting question, and this is what I want to discuss for the rest of this lecture. Where is the Newtonian angle? What I'm saying by this is the following. The way we set up our Einstein field equations was in such a way that we can recover Newtonian gravity. That in particular forced us to make a very specific choice for the coupling constant. And therefore we would expect that if we solve the relativistic geodesic equations like we have done, that somewhere the lowest order approximation for this should be a Newtonian result, because otherwise it doesn't really make sense. So we can ask ourselves now, hang on a minute, we have the expected result up here, the expected result that if there is no mass here, then there is no bending of light, and hence the trajectory is a straight line, and therefore there's no deflection angle. This is true in Newtonian physics and in general relativity. No mass, no action, nothing. And somehow it seems now when we extract the contribution linear and m, we already arrive at a general relativistic result. So how did we lose the Newtonian angle? And this is quite interesting here. And the interesting point is that in Newtonian physics, the photon, which you can think of as the light particle, the particle associated with the electromagnetic radiation that travels, or the light ray that comes from your light bulb, is massless. Hence, it should not interact, let's say interact with a gravitational field. However, there is a Newtonian prediction. So how can one do this? So this the back of the envelope argument is as follows. However, the photon or the radiation has energy. So the photon has energy, full stop. We also have that the speed of light or the speed of the photon is finite. So you can make the following kind of dirty calculation. You say, well, E photon is a half m effective c squared, because, well, let's say v squared, which you know is then c squared. So this is of course wrong what I'm writing here, but as I said, it is a dirty calculation to explain this argument. You could then hence define an effective mass for the photon, which is 2 times the energy of the photon divided by the speed of light squared. The units obviously match. However, you're somehow breaking the rules a little bit, because on the one hand, we know that the photon is massless. On the other hand, we say, well, if it has an energy and we interpret this energy as kinetic energy, then we can associate an effective mass to this. If we have an effective mass, then we can, of course, study its Newtonian trajectory, assuming it is a particle of this effective mass. So this breaks our modern point of view of physics, but is in a sense the way one can extract a result out of Newtonian physics. And with this argument in mind, I shall tell you that the Newtonian deflection angle has been known since the late 18th century. And it is given by delta phi Newton. It is 2m over r0, which is exactly half of the angle that we found, namely here. There's a factor of 4. The Newtonian calculation gives you a factor of 2, which means those angles differ exactly by a factor of 2. And all experimental evidence points very strongly towards the general relativistic result. Let me finish this lecture with a little comment on the precision of the data. That's sort of interesting. Sometimes people write something like this: delta phi equals alpha 4g m over c squared r dot, where clearly alpha equals 1 is gr and alpha equals 1/2 would be Newton. And the data I'm quoting is a paper from 1995. Let me just find the exact reference for you. The reference is Physical Review Letters, year is 1995, issue 71, and the page number is 1439. And they reported on this angle alpha, or not the angle, the number alpha that is used to parameterize this. And their data was 9998 plus minus 0008. So you see that we are, from an experimental point of view, very, very far away from Newton. And there is a very, very small chance that you might find a theory beyond general relativity that pushes this value below 1, but it is a very difficult call. So that is the light deflection discussed in general relativity, and we'll continue in our next lecture. Thank you.